So how are we going to find the steady state matrix of this matrix of transition probabilities P? Well, we have one equation to fall back on, and it's the following equation where you solve P times X is equal to X. And we already know what the X represents. Do we remember what it is? Well, let's cut right to it. So this is what it looks like when you use the equation P times X equal to X. And we're also given one equation. Well, yeah, because we know that x1 plus x2 plus x3, that these values have to be stochastic, meaning each column should add up to 1. So when we convert the matrix equation to a system of linear equations, we have to consider the equation that I've just written as well. So what is it going to look like when we convert from matrix to a system of linear equations? Well, we're going to grab the first row of the matrix of transition probabilities and multiply it by our common vector. And that's going to look like this. So we grab the first row of our transition probabilities, our matrix of transition probabilities, multiply it by the common vector, and this is what the equation should look like. And then we want each equation to be 0. We want it to equal 0. So we're going to subtract x1 on both sides. And what is that going to look like exactly? Well, it's going to look like this. When we subtract x1 from both sides, we get 0.6 x1 is equal to 0. So we already covered the first step, the first row of the matrix of transition probabilities, and the remaining rows, or it's a matter of rinse and repeat. So pause the video and figure it out for yourself, and I'll cut to what your system of linear equations should look like. So this is what your system of linear equations should look like. We have the 3 rows plus the 4th row reminding us that the steady state matrix is stochastic. And if you want to see the backbone of this solution, it should look something like this. And hopefully this clears things up. If you're still confused, drop a question in the comments and I'll be more than happy to help you out. So if we're given the following, do we have to use further algebra to find our solutions? Well, it turns out we don't have to do that, because we know that if we were to solve for x1 in the first row, we would get that x1 is equal to 0. And if we were to solve for x3, well, it turns out x3 is also equal to 0 if you observe the second and third equation. Actually, no. If you just observe the second equation, you're going to get that x3 is equal to 0. And then because we have x1 and x sub 3, we should be able to solve for x sub 2, which ends up being 1. Oh, my bad. Okay. And as a result, our solution ends up looking like this, where we have 0, 1, 0, and we're going to transpose that because, well, that's what it looks like in the original equation, where we had the steady state matrix as a common vector. Now, do you guys notice something about this solution? It turns out that this steady state matrix coincides with the second column of the matrix of the transition probability. Just thought that would be a worthy observation. Now, let's move on to the second example. So, we're still tasked with finding a steady state matrix, and we're given a hunk of a transition probability matrix. Okay, so it's the same as the exact example, but with a little more elbow grease. So let's convert this equation into a system of linear equations. So let's start off with the first row. So this is what it should look like when you multiply the first row of your transition of probability matrix by the column vector, and it should equal to the first row of the column vector past the equal sign. And if we were to have this equation equal 0, we'll subtract x of 1 on both sides. And what does that look like exactly? Well, it should look like this. So yeah, we got the first row out, and yes, for 0.5 I did have to make it a positive value because this would affect whether or not we would have a solution to the system. So we got the first row down, and now it's a matter of rinse and repeat. Go ahead and pause the video and repeat the pattern, and yeah, I'll cut straight to it. So this is what it should look like when we multiply each row within the P matrix to the column vector. And you gotta remember that our column vector is also stochastic. So what does that look like traditionally when it comes to a system of equations? Let's go ahead and grab what we got and put that in. So we have to solve for x 1, 2, 3, and 4. Yuck. But it turns out it's a lot easier than we realize. So let's look at the second and fourth equation. They're both equal to 0, and we can actually, and the 0.2 x of 1 cancels out. And when we're solving for x of 3, we can immediately deduce that x of 3 is equal to 0. If you don't believe me, do the work yourself, and the first person who writes out the solution for that gets their comment pinned. Now. Because we have x of 3, we can immediately solve for x of 1. We can plug in 0 for x of 3 in any of the 4 equations, and you'll get that x of 1 will be 0. Pause the video, you can confirm that yourself. And currently, you'll notice that in the system of linear equations, x of 2 and x of 4, well, they're 1 of 1. There's no solution for them. So what do we do exactly? What does that mean? So let's say that x of 4 is equal to t, where t can be any real number such that it is inclusively between 0 and 1 based on its stochastic nature. And because we substitute x for t, this indicates that x of 4 is equal to 1 minus t. And there you have it. We have the steady state matrix. And the steady state matrix can be denoted as such. So we have the steady state matrix, and in situations where you do have to substitute some variables for t, this indicates what exactly? Well, it simply shows that the Markov chain has an infinite number of steady state matrices. And in general, a regular Markov chain or an absorbing Markov chain with one absorbing state has a unique steady state matrix regardless of its initial state matrix. And further along that, an absorbing Markov chain with two or more absorbing states has an infinite number of steady state matrices, which also depends on the initial state matrix. And there you have it. We have just found the steady state matrices of absorbing Markov chains.